Good morning. So today we are going to discuss the displacement response of underdamped systems. In the last video we have seen what is a damped system and the damping ratio, and if the damping ratio psi is equal to 1, we call it as a critically damped system. If the damping ratio is more than 1, which is called an overdamped system, and we have derived expressions for the responses of critically damped system and overdamped system. Now we come to the third case, under damped system, that is the damping ratio is less than 1, or the damping present in the system is less than the minimum damping required for critical damping. Let us see what is the response of the structure. So the general expression for a damped free vibration is ms double dot plus cx dat plus kx is equal to 0. Then from that we have written this dividing by m. Then substituting x is equal to a raised to lambda t in this equation, we have got the roots of the equation as this. In this, if this term, this c by 2m is equal to omega, it's critically damped system. If c by m is more than omega, it is overdamped system. And now we are going to see the case when c by 2m is less than omega. The c by 2m is less than omega, or the damping ratio is less than 1. What is going to be the displacement response of this structure? So the c by 2m minus this term, I am going to make some substitutions like this. I am going to write let omega square minus c by 2m the whole square define a new term omega d, where this omega d is called the damped frequency. Omega suffix d is called the damped frequency of the system, whereas this omega is the natural frequency. Natural frequency is the frequency of vibration of a free vibration system without any damping. So omega d I have defined like this, or we can rewrite it like this: omega square minus, we have written here c by 2m omega is the damping ratio. C by 2m omega is the damping ratio, or C by 2m in terms of the damping ratio, it is psi omega. So omega square minus psi omega the whole square is equal to omega d square, or omega square into 1 minus psi square is omega d square, or this damped frequency omega d is omega in the root of 1 minus psi square. So the damped frequency, or the frequency of a system with damping, is in terms of the natural frequency of the system omega in the root of 1 minus psi square. In this, the value of psi is usually less than 1. The percentage damping present in the system is about 10%, 20% normal values. So this term is always going to be less than 1. So we can say the damped frequency will be less than the natural frequency. So a system with some amount of damping present in it, the natural frequency, the frequency of the damped system will be slightly less than the natural frequency of the system, that is a system without any damping. Normally this is very small, psi will be very small value, so that approximately we can, for even if we take that the damped frequency is equal to the natural frequency, doesn't matter at all. So the damped frequency is omega d into root of omega and root of 1 minus psi square. Now we come into this roots. These two roots, lambda 1 comma 2, the roots lambda 1 comma 2 is equal to minus c by 2m plus or minus square root of minus omega d square. Omega square minus c by 2m is omega d square. So this is minus omega d square. So this can be written as minus c by 2m plus or minus I omega d. So this is equal to minus psi omega, c by 2m is psi omega plus or minus I omega d. So the two roots are two different roots. First root is minus I omega plus I omega d, and the second root is minus I omega minus I omega d. So there are two different roots, and the solution to this equation, is of the form, x is equal to a1 e raised to lambda 1t plus a2 e raised to lambda 2t. So this is the solution of the equation a1 e raised to lambda 1t plus a2 e raised to lambda 2t. In this, for lambda 1 we substitute psi omega plus or minus plus I omega. Lambda 2 is substitute minus I omega minus I omega d. Substituting in this equation, x is equal to a1 e raised to minus I omega plus I omega d t plus a2 e raised to minus I omega minus I omega d t. Now we expand it, e raised to minus I omega t plus e raised to I omega dt, etc. You expand this, and finally we get a solution of the form x is equal to e raised to minus I omega t into c1 cos omega dt plus c2. This expanding the terms and clubbing similar terms, all these steps I am avoiding here. The final step you will be getting as x is equal to e raised to minus I omega t into c1 cos omega dt plus c2 sin omega dt. Our aim is to find the value of c1 and c2. The two constants can be evaluated from the initial conditions. That is, at x is equal to, at time t is equal to 0, the initial displacement x is equal to x0. Substituting in this, and t is equal to 0, x is equal to x0, e raised to 0 will become 1, c1 cos omega t will become 1, c2 0. So c1 will get is equal to x0. Now differentiating this, x dash dx by dt is equal to, first into differential second, you apply the product rule, first into differential second is c1 sin omega dt into omega plus c2 cos omega dt into omega d, and also omega d. So first into differential second plus second into differential first, e raised to minus psi omega t into minus psi omega. This is the differentiation. Now put t is equal to 0 in this expression. Putting t is equal to 0, this will become x0 dash At time t is equal to 0, x velocity is x0 dash. This will become 1. See, this term becomes 0. This will become c2 omega d. What about this is c2 omega d plus this here, it will become, putting t is equal to 0, it is c1 e raised to minus, that will become 1 minus I omega. But c1 value is, we know it is x0. Substituting here we will get c2 is equal to x0 dash plus psi omega x0 divided by omega d. C1 is x0, so we'll get C2 value is equal to x0 dash plus I omega x0 divided by omega d. Now this equation solution. So the final solution is x is equal to e raised to minus psi omega t into x0 cos omega dt plus x0 dash plus theta omega psi omega x0 divided by omega d into sin omega dt. So the solution of this equation is x is equal to e raised to psi omega t into, when there was no damping, it was x is equal to x0 cos omega t plus x0 dot by omega sin omega t. Here it is x0 cos omega d t x0 dot plus theta omega x0 by omega d into sin omega d omega dt. So what about this expression? This is a solution. What is the physical significance of this equation? The response of an underdamped system contains the terms cos omega d and sin omega d. So it is oscillatory. It contains periodic terms. So the motion is oscillatory motion, and there is a term e raised to minus sin omega t. It's an exponential term. It's a negative. So the motion of an underdamped system is oscillatory, and at the same time it exponentially decreases. So if we plot it, the response diagram, the displacement response, so if you plot the response of an underdamped system according to this e raised to psi omega t exponential decrease, the amplitude, so this is the amplitude, the maximum displacement, here it's the maximum displacement. So it starts from an initial displacement of x0, an initial velocity x0 dash, it undergoes oscillatory motion, and we can see that the amplitude decreases in each cycle. So this time for one cycle is called the time period, the damped time period. So for an underdamped system, this is the response x versus t. The response of an underdamped system is oscillatory, and as time it is exponentially decreases and amplitude of vibration goes on reducing and finally it decays out. Now this reduction in amplitude, it is a measure of the damping present in the system. So by conducting experiments, we can give some source of vibration and make it vibrate. And in the experiments, we will get this from the oscillograph, we will get this displacement time history. By measuring the amplitudes, we can get what is the damping present in the system. So now we have seen an underdamped system, the motion is oscillatory. What about the previous case? In the previous case, in an critically damped system, the system starts from the initial displacement, it suddenly comes back to the neutral position. This is underdamped. Critically damped. In the case of that is psi is equal to 1. When psi is greater than 1, overdamped system, it starts from the initial position and it slowly comes back to the neutral position. So this is when it is an overdamped system. Psi is greater than 1, and this is the case when psi is less than 1, underdamped. So the response of the structures to a critically damped system, it is not oscillatory, it suddenly comes back to the neutral position once it is disturbed. In the case of overdamped system, it's from the initial displacement, it exponentially decreases, and as time tends to infinity, it comes to rest. In the case of an underdamped system, the motion is oscillatory and its amplitude reduces with time. Okay, now we make use of the displacement response of an underdamped system. From that, how to arrive at the damping present in the system. I have told you in the response diagram, it gives us how the amplitude decreases. It is a measure of the damping present in the system. So this is the displacement response of an underdamped system. Let us say at any time t, the amplitude is say x suffix n. After one cycle, from here to the maximum bottom, then to the top maximum. After one cycle, the time is called the damped time period. Time for one cycle is period. The amplitude is say xn plus 1. So if you measure these two amplitudes, xn and xn plus 1. Now the term logarithmic decrement is delta is nothing but the natural logarithm of two successive amplitudes. The natural logarithm of two successive amplitudes is called as logarithmic decrement. Now this is used for measuring the damping. Let us see how we get an expression for this. Xn is the displacement at time t. So it is equal to, we have just derived, e raised to minus psi omega t into c1 cos omega dt plus c2 sin omega dt. Now xn plus 1. What is xn plus 1? Xn plus 1 is the amplitude at what is the time now? At that t plus td. When the time is t plus td, amplitude at that time is called xn plus 1. So xn plus 1, in the place of t you substitute t plus td. E raised to minus psi omega t plus td c1 cos omega d t plus td plus c2 sin omega d t plus td. Now let us do xn by xn plus 1. This by this, equation 1 by equation 2, dividing, we will get Before that, I can one more step I have to write here. We can expand this and write it. So this can be written as e raised to minus psi omega t into e raised to minus psi omega td. What is this t? Time period can be written in terms of the natural frequency. Time is equal to 2 pi by omega. The period can be written as 2 pi by omega into C1 cos omega d t plus 2 pi by omega d C2 sin omega d t plus 2 pi by omega d. Now I will do xn by xn plus 1. So dividing this by this, here these two gets cancelled. E raised to minus psi omega into 2 pi by omega d. Here C1 cos omega dt plus C2 sin omega dt. Here you see it is cos omega dt plus 2 pi. Cos theta plus 2 pi is the same as cos theta. Similarly, sin omega dt plus sin omega d plus 2 pi. So this can be rewritten as, when you divide this by this, it will be, so when you do, because this term and this are the same, because cos t plus 2 pi is the same as cos omega dt. So dividing xn by xn plus 1, we get minus psi omega into 2 pi by omega d, or delta is natural logarithm of xn by xn plus 1. So taking natural logarithm of this, it will become psi omega into 2 pi by omega d. Psi omega 2 pi by omega d is, we have written, it is omega into root of 1 minus psi square. These two gets cancelled, or delta is equal to 2 pi psi divided by root of 1 minus psi square. Psi is usually very less than 1. Normally the value is 0.1 and maximum 0.2. So if there is no harm, so that 1 minus psi square can be approximated to 1, or delta is equal to 2 pi psi. What is psi? Psi is the damping ratio. So if you measure two successive amplitudes, check the natural logarithm of it. That will be delta. So from that we get the damping ratio psi is equal to delta by 2 pi. Thus, we can get a measure of damping present in the system from the measurement of successive amplitudes. Okay, thank you for the day. In the next video, we will see the numerical examples based on this damped free vibration. Thank you.